In this video, you're going to learn about how to master kinematic curves in less than 20 minutes. Motion graphs can be pretty confusing, but if you're equipped with the right ideas and strategies, they can be simplified. So I'm going to break down these graphs in detail with a lot of tips and tricks. Let's go. On the screen, we have our three main types of motion graphs. We have an x versus t graph, a position versus time graph, a velocity versus time graph, and an acceleration versus time graph. What we're going to do is we're going to start off with the most basic types of motion to develop the concepts for how to analyze, draw, and just understand these graphs inside and out. All right, now the most basic kind of motion we have is a constant positive velocity. This would be one where if you were to walk in front of, say, something like a motion detector, and it would track you for every second you moved, we'll say 1, 2, 3 seconds, it's going to show your position as time elapses. So let's say for this one, you end up moving 1 meter per second. You should have a nice straight line, which shows you that's a constant positive velocity. Now, without even knowing the number, you can still do your second graph, but I'm going to go ahead and use the number for my slope in order to help us understand the velocity versus time graph and then the acceleration versus time graph. Now, typically, if you knew that this was a constant positive slope, the rate that the position changes per time is known as the velocity. So let's go ahead and make a note of that. If you find the slope of the position versus time graph, that is going to give you the velocity. Now, since you have a constant positive slope, we then have a constant positive velocity. Now, if you were to know the number, you could actually solve for the slope using delta y over delta x, and then find out it's going 1 meter per second. Now, because it's a constant negative slope, or excuse me, a constant positive slope, then we want to make sure our velocity is nice and constant, which means it stays the same, showing that it's traveling 1 meter for every second that you move. Now, acceleration is measuring the rate that velocity changes over time. In that case, if we were to analyze this slope for the velocity versus time, there is no slope. The slope is 0. So the acceleration would be right on the x-axis to represent 0 meters per second squared, which means that you're adding 0 meters per second, which obviously means you're not changing the velocity at all. So if you have any sort of flat line on a velocity versus time graph, that means the acceleration is always going to be 0. That also means that if you have any straight line on your position versus time graph, whether it's slanted positive, negative, or completely flat, that would mean your acceleration is 0 because those are all constant velocity curves. Now, if you were to have something like this, that just means that you're moving in the other direction. You're starting at 2 meters and you're working your way back to 0. So that doesn't mean anything about how fast it's going or what it's doing besides the direction. So we call that the negative direction, which could be instead of going right, you're going left, or instead of going east, you're going west. Now for this one, if you're going back in the negative direction, you are decreasing your velocity, or excuse me, decreasing your position. If I were to find the slope for this one, the delta y is -2 because it drops back 2 in 2 seconds. So we'll call this a -1 meter per second slope. In this case, your line would be a constant negative velocity underneath the x-axis. Okay, and if you were to draw the acceleration versus time graph, that would definitely be right on 0 again because there is no change in the meters per second per second. All right, so to conclude our first little portion of the video, if we have any sort of straight line of any sort for our first graph, that means it is for sure going at a constant velocity because the slope or steepness of the slope remains constant. When we slide to the velocity versus time graph, this will definitely be a flat line. Flat showing that the speed at which it's moving or the velocity in which it's moving stays completely constant at a positive or negative velocity depending on which direction it's going based on the slant from your position versus time graph. And then for this one, It is 0 every single time for anything that's going at constant velocity. Doesn't matter if it's going 1 meter per second or 100 meters per second. If there is no change, then there is no acceleration, because acceleration is the rate that velocity changes. Now, one final point I wanted to make before we move to a new screen is that if the steepness of the slope changes, the steepness is representative of how fast something is moving. Okay, for example, if we have a new graph that looks like this, it's straight, so it's constant velocity, but it happens to be going up 3/1. That would be 3 meters per second. Okay, now if it is a steeper slope, that's showing you that it's gaining position quickly as it's vertically rising in a shorter period of time. In that case, you would still have a flat line, but then you just want to make sure that you would sketch it farther from the x-axis, because this is 0, right? So if it's going faster in the positive direction, that line is going to rise higher away from the x-axis. If that were, say, maybe a negative 3 meter per second, that would actually go lower, further away from the x-axis, to show it's going faster in the negative direction. Remember, -3 is faster than -1, because negative is just telling you the other direction. So it's still talking about the amount of meters per second, so -3 meters per second would definitely be faster than -1 meter per second. All right, that covers our first portion. Now moving on, if we have a curved position versus time graph, we now have a slope that's changing. If you analyze the slope at different points, we'll call it the beginning, middle, and end. We maybe have a 0 slope here. Over here we have a, we'll say, medium positive slope, and then over here we have a much steeper positive slope. So we'll call that a big positive, and we'll make our positive a little bit larger. Okay, earlier we said the slope, or the rate at which the position changes per time, always tells you the velocity. Now, if we were to track that, every little tiny time increment, it's changing. It's not really changing 1, 2, 3, it's just changing the entire time. But if we just use those 3 checkpoints, we can learn about our velocity. So each of those slopes represents a velocity. So we have 0, a medium positive number, and then a higher positive number. And if we connect those dots, we have a constant positive slope to show that the object is actually speeding up. So if you see any kind of curved line here, we for sure know that the object is accelerating. Okay, we don't know if it's speeding up or slowing down necessarily. We're going to get to that point in a little bit, but we know that the line is definitely not straight, which means that the rate at which it's moving is changing, therefore it must be accelerating. Now, what I'd be looking at is if the slope is getting steeper or more flat. This one is becoming more steep, which means the value of the velocity is increasing, so I'm going to slant the line away from 0. And remember, if we go from our velocity to our acceleration graph, again, we're analyzing the slope because the rate that the velocity changes per time is the acceleration. This is a constant positive slope, so we have a constant positive acceleration. Okay. Now say, for example, that acceleration was, I'll just come up with a number 2. That means 2 meters per second, or 2 meters per second squared. So if that were the acceleration, this one would go from 0 to 2 to 4, and then so on, 6, 8, 10, if the time kept on continuing. Now, if we had a different case where it was slowing down, then we would have something that looks like this. Now, that curve over there it's definitely curved, so it's accelerating. But this one, if we analyze the slopes, starts out very steep, goes to a medium one, and then goes sort of flat towards the end. So we're going to call that big positive, medium positive, and this one maybe just a tiny little positive. Okay, so if we were to track this one, it would do the exact opposite. It would start big positive, medium, and then small. We'll just say that it goes all the way pretty much to 0. Okay, that means it's slowing down. So anytime something is slowing down, you want to make sure you slant it towards 0. So in this case, again, we had something flattening out. If it starts to get more flat, that means it's slowing down. Hey, the first one we looked at, it was getting steeper. That means it's speeding up. So let's go ahead and make a note of that. All right, I didn't leave myself a lot of space there, but if the line is getting steeper, it is speeding up. Okay, both of these remain in the positive region of the velocity versus time graph above the x-axis because both of them are rising up on the position versus time graph. So if they're rising up on the position versus time graph, it's going to stay up in this positive region over here. All right, now going to our red velocity versus time graph, the one that's slowing down, that one has a constant negative slope. So we have a constant negative acceleration. So it's going to be right down there. So our acceleration time graphs are now definitely not going to be on 0. They're going to be on the positive and negative depending on how the velocity is changing on this graph right over here. All right, now moving on to our very last one. All right, for our very last one, we have something that's curving down this way. So we have something that's definitely now moving in the negative direction because it's dropping down on our graph. If we analyze the slopes, we can spot it at the beginning, middle, and end again. And we have a flat 0 slope. This one is a medium negative, and this one is much more steep, more vertical, big negative. So if we were to use those 3 checkpoints for our velocity versus time graph, I'm going to go with 0, medium negative, larger negative. And then we can connect the lines that way. And we have a constant negative slope for our velocity versus time graph. Okay, again, for more emphasis, those slopes or the rate of change on your position versus time graph are representative of your velocity. Now, the negative one tends to be a little tricky. This one is going downwards, which makes people maybe think that it's slowing down, but the slope is getting steeper, so the amount that it's jumping downwards on the graph is actually increasing. It's going faster. Now, if it's speeding up, remember, that means steeper slopes. Okay, now then you might be asking the question, if it's speeding up, why is the line slanted down? Okay, it's slanted down away from 0. That's the rule. If it's slanting away from 0, the number is getting increasingly faster. It's going from, we'll say, 0 to -5 to -10. Remember, the negative is just showing the direction. It's going to the left as opposed to going to the right or going backwards instead of forwards. So that negative is just telling you the direction, but it is still going 5 meters per second now and 10 meters per second afterwards, which shows that its speed is increasing. And we have a constant negative slope, so we have a constant negative acceleration. This would be -5. Okay, so remember the meaning of that -5 is saying that it's a -5 meter per second change every second, which is commonly written as -5 meters per second squared. Okay, which means you're subtracting 5 meters per second. But if you're subtracting 5 from an already negative number, it just becomes an increasingly larger negative number. So that's why the negative acceleration speeds up this already negative velocity from -5 to -10 and -15, so on. Now, if the graph were to be slowing down, remember our rule earlier is that it would be coming down, but the curve would be flattening out. Okay, so if we analyze that slope, it goes very steep, big negative slope in the middle, medium negative, and at the end, it looks like it's hitting about 0. Okay, the rule for showing something that's slowing down isn't a negative slope, it's always slanting towards 0. So I got big negative, medium negative, 0. Okay, we have a positive slope slanting towards 0, showing that negative velocity is decreasing and then going towards 0, which is completely stopped. And we have a constant positive slope, so we have a constant positive acceleration. In this case, say for example, we have an acceleration of +5, and we maybe go from -10 to -5 to 0, then if you add +5 meters per second to a -10, it changes it to -5. If you add another +5 to the -5, it makes it 0. So that positive acceleration is going to be slowing down that negative velocity because the force would be pushing in the negative direction, or excuse me, the positive direction. All right, so to sum things up, if it is steeper, then it is speeding up, or if it's getting steeper, excuse me, if it's getting more flat, that means it's slowing down. I didn't space this out very well. That means that it's slowing down. Okay, if you want to see which direction it's going, it's pretty easy because if it's rising up on the graph, it's positive. If it's moving down the graph, it's negative. Okay, remember from the very first screen, if it's anything perfectly straight, whether it's slanted or completely flat, that's a constant velocity. All these curved ones, you're immediately noticing it's accelerating, and then you want to pay attention to whether it's getting more steep or more vertical to see if it's speeding up or becoming more flat towards the end, which means it's slowing down. Okay, in that case, when you go to your velocity versus time graph, if it's speeding up, then you want to make sure it slants away from 0. And then if it's slowing down, then you want to slant it towards 0. Okay, as I said before, the tendency is to make speeding up a positive slope and slowing down a negative slope, which sounds like it makes sense, but not particularly for our velocity versus time graph, so you want to make sure you slant away from 0 or towards 0. When you go to your acceleration time graph, if it's a constant velocity, it's going to be dead on 0 if it's constant velocity. If it's anything else that's speeding up or slowing down, you will for sure have a constant positive or constant negative slope, assuming we're talking about uniform acceleration. So I hope that helps with understanding, analyzing, interpreting position, velocity, and acceleration time graphs. Thanks for watching and listening.